Where did 3I-ATLAS really come from? The official answer is somewhere among 400 billion stars. But the real mystery runs deeper. This interstellar visitor didn't just wander into our solar system. It arrived with a trajectory so precisely calculated that astronomers are questioning whether natural cosmic mechanics can explain it. Racing from the direction of galactic center at impossible speeds, carrying chemical signatures of an alien world, 3I-ATLAS might be more than random debris ejected from another star system. Its origin story could rewrite everything we know about what travels between the stars. Stay until the end to discover the evidence that's making scientists wonder if this visitor chose its birthplace, or if its birthplace chose us. Before we trace this cosmic mystery back to its source, drop a comment. Where are you watching from, and what's your local time? It's remarkable that people worldwide are exploring these same profound origin questions together. Now, prepare yourselves for the cosmic journey ahead. We begin. Part 1. Where did 3I-ATLAS really come from? On July 1st, 2025, astronomers at the Atlas facility in Chile spotted something that shouldn't have been there. A faint smudge of light, moving against the star field in a way that defied everything we thought we knew about our cosmic neighborhood. Within days, the calculations were undeniable. This wasn't another asteroid from our solar system's debris field. This wasn't even a comet from our distant Oort cloud. This was 3I-ATLAS, the third confirmed visitor from another star system. Only twice before in human history have we witnessed such an event. First came 1I, Oumuamua, in 2017, that tumbling cigar-shaped mystery that sparked 1,000 theories and just as many arguments. Then 2I, Borisov, in 2019, which behaved like a textbook comet but carried the chemical fingerprints of an alien world. Now, 6 years later, we have our third interstellar guest. But 3I-ATLAS is different. Where Oumuamua remained stubbornly mysterious and Borisov played by the rules, this new visitor seems to be writing its own playbook. The central question isn't just where it came from, it's whether it came from anywhere natural at all. Consider the mathematics of coincidence. In a galaxy containing 400 billion stars, spread across a disk 100,000 light-years wide, what are the odds that an interstellar object would choose a path that skims so perfectly along our solar system's ecliptic plane? What are the chances it would pass within spitting distance of not one, not two, but multiple planetary orbits? Some calculations put these odds at 1 in 500. Those aren't impossible odds, but they're the kind that make scientists pause and double-check their work. The stakes couldn't be higher. If 3I-ATLAS is what it appears to be, a natural comet ejected from another star system, then it represents our best opportunity yet to study the chemistry of an alien world without leaving Earth's vicinity. Its composition could tell us how other planetary systems form, how different stellar environments forge different types of ice and rock, how the galaxy's older neighborhoods compare to our own 4.5 billion-year-old corner of space. But if it's something else entirely, well, that changes everything. The object is following what astronomers call a hyperbolic trajectory. Imagine a one-way freeway exit that never loops back. It's moving at 61 kilometers per second relative to our Sun, roughly 130,000 miles per hour. That's the kind of speed you only get when you've been wandering the galaxy for eons, picking up gravitational nudges from countless stellar encounters like a cosmic pinball. We have until late October, when 3I-ATLAS reaches its closest approach to the Sun at a distance of 1.4 astronomical units, just inside Mars's orbit. Then it will swing around our star and head back out into the void, never to return. This is our window, our chance to solve a mystery that began somewhere among the stars and ended up in our telescopes. The evidence will come from multiple sources. Discovery kinematics tell us about its origin and trajectory. Coma and tail behavior reveal how it responds to solar heating. Volatile inventory, the specific gases it releases, provides a chemical fingerprint of its birthplace. Orbital alignment with our ecliptic raises questions about natural versus artificial guidance, and any non-gravitational accelerations could betray hidden propulsion systems. By the time you hear this story, some of these questions may already have answers. Perihelion occurs on October 29th and 30th, 2025. The post-perihelion re-emergence window in early December represents our final chance to observe this visitor before it fades into interstellar darkness. What would constitute proof of natural origin? A water-heavy, carbon-poor chemistry consistent with formation around an older metal-poor star. Smooth, predictable outgassing behavior that follows the laws of physics without surprises. A trajectory that, while unusual, can be explained by gravitational mechanics and billions of years of stellar encounters. What would suggest something more extraordinary? Sustained, directed changes in velocity that can't be explained by outgassing. Narrowband radio emissions. Radar signatures inconsistent with a loose pile of ice and rock. Chemical compositions that don't match any known natural process. The safety context is clear. 3I-ATLAS poses no threat to Earth. Its closest approach to our planet will be roughly 1.6 to 1.8 astronomical units, a comfortable margin that makes this purely a scientific encounter. This isn't about planetary defense or evacuation plans. This is about understanding our place in a universe that keeps sending us messages we're only just learning to read. Think of 3I-ATLAS as a time capsule from the galaxy's older neighborhoods. Its chemistry encodes the story of stellar evolution, planetary formation, and the violent processes that fling debris between star systems. Whether it's a scout with a return address or simply a snowball with an exotic pedigree, it represents our best sample by light of how the universe builds worlds beyond our own. The journey to answers begins with a simple truth. Extraordinary claims require extraordinary evidence. We'll keep an open mind while demanding the highest standards of proof. In the next few months, as Earth's most powerful telescopes turn their attention to this cosmic visitor, we may finally learn whether we're alone in crafting machines that traverse the space between stars. Part 2. A bullet through the solar system. The alert came through at 3:47 a.m. Chilean time on July 1st, 2025. Dr. Robert Werrick, the same astronomer who discovered 1I Oumuamua 8 years earlier, was monitoring the ATLAS Chile telescope feed when a particular pixel sequence caught his attention. Something was moving against the background stars, something that didn't belong to any catalogue of known solar system objects. Within hours, follow-up observations from telescopes around the world began painting a picture that sent shockwaves through the astronomical community. The trajectory calculations were unambiguous. This object was moving on a hyperbolic path, not the elliptical orbits of planets and asteroids, not even the stretched ellipses of long-period comets from our own Oort cloud. This was the signature of an interstellar visitor. The numbers told a story of cosmic violence. 3I-ATLAS was traveling at approximately 60 to 61 kilometers per second relative to our Sun, roughly 130,000 miles per hour. To put that in perspective, our fastest spacecraft, Voyager 1, moves at about 17 kilometers per second. This object was moving more than 3 times faster than humanity's most ambitious attempt to reach the stars. That velocity alone ruled out any solar system origin. Objects from our Oort cloud, even those on the most extreme trajectories, rarely exceed speeds of 45 kilometers per second relative to the Sunday. The mathematics were clear. This visitor had been traveling through interstellar space for millions, possibly billions of years, slowly accelerated by gravitational encounters with other stars, until it reached this tremendous velocity. The trajectory itself told an equally compelling story. 3I-ATLAS was approaching from the southern sky, roughly in the direction of the constellation Sagittarius, toward the center of our galaxy. But its orbital inclination was the real surprise. Approximately 175 degrees, meaning it was traveling in a highly retrograde direction relative to the plane of our solar system. Imagine our solar system as a racetrack where all the planets circle counterclockwise. 3I-ATLAS was racing clockwise at maximum speed. This retrograde motion provided another clue to its interstellar nature. Objects that formed in our solar system tend to orbit in the same direction as the planets, a consequence of the rotating disk of gas and dust from which we all formed 4.5 billion years ago. A retrograde orbit this extreme suggested an origin far from our cosmic neighborhood. The geometry of the encounter was both spectacular and scientifically fortuitous. Unlike 1I, Oumuamua, which was discovered only days before its closest approach to the Sun, 3I-ATLAS was spotted months in advance. This early warning gave astronomers unprecedented time to plan comprehensive observations with every available instrument. The timeline unfolded with clockwork precision. From its discovery in July, 3I-ATLAS would continue its inbound journey through the summer and fall of 2025, reaching perihelion, its closest approach to the Sun, on October 29th and 30th, at a distance of approximately 1.4 astronomical units. That's just inside the orbit of Mars, close enough for detailed study but far enough to ensure safety. For Earth, the geometry was particularly favorable. During the critical observation window, our planet would maintain a comfortable distance of 1.6 to 1.8 astronomical units from the visitor. No impact risk, no gravitational perturbations, just the perfect setup for extended scientific observation. The retrograde trajectory would carry 3I-ATLAS in a steep dive through the inner solar system, passing near the orbital regions of Venus, Earth, Mars, and Jupiter before swinging around the Sun and heading back out toward interstellar space. Each planetary encounter, while distant, would provide opportunities to study the object under different lighting conditions and gravitational influences. What made this discovery truly remarkable was not just the early detection, but the brightness. Unlike 1I, Oumuamua, which remained frustratingly faint and difficult to study, 3I-ATLAS was bright enough for detailed spectroscopic analysis. This meant that for the first time, astronomers would have the opportunity to perform comprehensive chemistry on an interstellar visitor. The implications were staggering. Every previous attempt to understand the composition of interstellar objects had been hampered by late discovery and insufficient brightness. 1I, Oumuamua, had slipped through our solar system before we could properly analyze its surface composition. 2Y, Borisov, while better observed, was studied primarily during its approach phase. 3I-ATLAS promised to be different, bright enough, early enough, and long enough in our sky to provide the definitive chemical fingerprint of another star system. NASA's Hubble Space Telescope had already captured preliminary images by July 21st, showing a teardrop-shaped dust coma streaming away from the object's sunward side. The very presence of this coma was significant. It proved that 3I-ATLAS was actively sublimating ice and releasing dust, behaving like a traditional comet, despite its exotic origin. The discovery also represented a milestone in our growing catalogue of interstellar visitors. With 3 confirmed objects in 8 years, 1I, Oumuamua in 2017, 2I, Borisov in 2019, and now 3I-ATLAS in 2025, astronomers were beginning to discern patterns in what had once seemed like isolated anomalies. Each discovery built upon the last. Oumuamua taught us that interstellar objects could be found if we looked carefully enough. Borisov showed us that some of these visitors behaved like familiar comets. Atlas promised to bridge the gap between mystery and understanding, offering our most detailed look yet at the composition and behavior of matter from beyond our solar system. The safety message could not be overstated. Despite the dramatic speeds and exotic origin, 3I-ATLAS posed absolutely no threat to Earth or any other planet. Its trajectory had been calculated with extreme precision, and every model confirmed that this would be a purely scientific encounter. The closest approach to Earth would occur at a distance nearly 200 times greater than that between Earth and the Moon. As summer turned to fall, and 3I-ATLAS continued its inexorable approach toward perihelion, the astronomical community prepared for what might be the most comprehensive study of an interstellar object in human history. The stage was set for a cosmic forensics investigation that would either confirm our understanding of how natural objects travel between stars, or challenge everything we thought we knew about what moves through the galaxy's dark spaces. Part 3. Skimming the ecliptic. Coincidence or design? There's an invisible dinner plate in space, roughly centered on our sun, that defines the architecture of our solar system. Astronomers call it the ecliptic plane, the flat disk containing the orbits of all major planets. For 4.5 billion years, this plane has organized the dance of worlds around our star, from Mercury's tight embrace to Neptune's distant waltz. 3I-ATLAS, however, chose to ignore conventional choreography. While the object's trajectory is indeed retrograde, moving clockwise when everything else moves counterclockwise, its orbital plane lies within just 5 degrees of our ecliptic. This means that despite traveling backward relative to planetary motion, it's skimming along the surface of our solar system's dinner plate rather than diving through it at a steep angle. The mathematics of this alignment have sparked intense debate in astronomical circles. Dr. Abraham Loeb of Harvard, along with colleagues Sean Hibbard and Adam Crowell, published calculations suggesting that such an alignment occurs by chance in roughly 1 out of 500 interstellar encounters. Those aren't impossible odds, but they're low enough to raise eyebrows among scientists who've learned to be suspicious of convenient coincidences. The geometry becomes even more intriguing when you examine the specific planetary encounters. 3I-ATLAS doesn't just skim the ecliptic, it passes through the orbital neighborhoods of Venus, Earth, Mars, and Jupiter in sequence. Not close encounters, mind you, but passages through the general vicinity of each world's gravitational influence. It's as if someone plotted a course designed to sample the environments of multiple planets without actually visiting any of them. This multi-planet proximity forms a central pillar of what Loeb and his colleagues term the artificial origin hypothesis. Their reasoning follows a kind of reverse engineering logic. If you were designing a probe to study our solar system, what kind of trajectory would you choose? A path that maximizes planetary encounters while minimizing fuel requirements. A route that takes advantage of our system's natural geometry to achieve multiple objectives with a single flyby. The timing adds another layer to the mystery. 3I-ATLAS reaches perihelion, its closest approach to the Sun, at a point in its orbit where our star lies between the object and Earth. This configuration, known as superior conjunction, would be ideal for what engineers call a reverse Oberth maneuver. If the object were indeed artificial, this would be the perfect moment to fire engines while hidden behind the Sun, using solar gravity to amplify any velocity changes. The speculative paper explores these possibilities with the careful language of scientists walking on thin ice. Loeb and his colleagues present their work not as evidence of artificial origin, but as a checklist of tests, a framework for distinguishing between natural and engineered trajectories. Their calculations include projected arrival windows for Earth and Jupiter, encounters if powered maneuvers were performed during perihelion, though they emphasize these remain purely hypothetical scenarios. It's crucial to understand what this research represents and what it doesn't. The RX-Eve preprint has not undergone peer review, making it exploratory rather than definitive. The authors themselves acknowledge that low-inclination interstellar encounters must occur occasionally by pure chance, and that 3 confirmed visitors represent far too small a sample to establish statistical significance. The mainstream counterargument relies on selection effects and statistical inevitability. With hundreds of billions of stars in our galaxy, and trillions of opportunities for gravitational encounters over cosmic time, some interstellar objects will inevitably enter our solar system along seemingly convenient trajectories. The fact that we've observed one such case out of 3 total visitors might simply reflect the universe's capacity for producing apparent patterns from random processes. Furthermore, the early speculation about 3I-ATLAS showing no coma, which initially supported artificial origin theories, has been thoroughly debunked by subsequent observations. Hubble Space Telescope images clearly show dust and water vapor streaming from the object, demonstrating genuine cometary activity that strongly supports natural formation and composition. The critical test lies ahead. Natural comets follow predictable patterns of outgassing as they approach the Sun, creating small but measurable changes in trajectory. These non-gravitational accelerations arise from the rocket effect of sublimating ice. Essentially, the comet pushes itself around by venting gas in preferential directions. If 3I-ATLAS is natural, its post-perihelion trajectory should show exactly these kinds of changes, and they should correlate precisely with observed outgassing activity. Artificial objects, by contrast, might show trajectory changes that don't match outgassing patterns, sudden velocity adjustments, course corrections that occur during solar conjunction when direct observation is impossible, accelerations that persist long after cometary activity should have ceased. The visual metaphor is striking. Imagine our ecliptic as a cosmic highway, and most interstellar visitors as cars taking random exit ramps at unpredictable angles. 3I-ATLAS, however, appears to have merged into traffic, followed the main thoroughfare past multiple planetary neighborhoods, and chosen its exit timing with remarkable precision. This geometric argument represents just one piece in a larger puzzle that includes chemistry, dynamics, and timing. The ecliptic skimming trajectory is certainly unusual, but unusual isn't synonymous with impossible. The universe has had billions of years to produce coincidences that would seem remarkable from our limited human perspective. What transforms this from speculation into science is the existence of testable predictions. If 3I-ATLAS were artificial, its post-perihelion behavior should deviate from pure cometary physics in measurable ways. If it's natural, the trajectory should follow gravitational and outgassing mechanics with boring predictability. The resolution may come sooner than expected. As 3I-ATLAS emerges from solar conjunction in early December 2025, precise astrometry will reveal whether its outbound trajectory matches theoretical models or contains surprises that challenge our understanding of interstellar visitors. Until then, the ecliptic skimming geometry remains a tantalizing mystery card in the cosmic deck, low enough probability to demand attention, but not so low as to defy explanation through natural processes. Part 4. Older than our Sun, a wanderer from the galactic thick disk. To understand where 3I-ATLAS came from, we need to think beyond individual star systems and consider the architecture of our entire galaxy. The Milky Way isn't a uniform disk of stars, it's a layered structure, with different populations representing different epochs of cosmic history. The kinematics of 3I-ATLAS, its speed and direction relative to our local neighborhood, point toward an origin in what astronomers call the galactic thick disk. This is the older, more diffuse population of stars that sits above and below the thin disk where our Sun resides. While our solar system formed roughly 4.5 billion years ago during a relatively recent era of star formation, the thick disk contains stellar populations that are significantly older, some approaching the 10 billion year age of our galaxy itself. This age difference matters enormously for understanding 3I-ATLAS's composition and behavior. Stars that formed early in galactic history did so from gas clouds with very different chemical compositions than those available today. Heavy elements, what astronomers call metals, meaning anything heavier than hydrogen and helium, were far less abundant in the early universe. Iron, silicon, carbon, and nitrogen had to be forged in stellar cores and distributed by supernovae, a process that took billions of years to enrich the galaxy's gas supplies. A comet that formed around an ancient metal-poor star would therefore have a very different chemical fingerprint than one that formed in our contemporary stellar neighborhood. We would expect such objects to be water-heavy but carbon-light, reflecting the limited availability of complex carbon compounds in the early galactic environment. This prediction aligns remarkably well with the preliminary observations of 3I-ATLAS, which show strong water signatures but unusually weak carbon-bearing molecules. The object's trajectory provides additional clues about its ancient wandering. 3I-ATLAS entered our solar system moving away from the galactic center, but its path doesn't align clearly with any known stellar stream or moving group. This suggests a complex history of gravitational encounters, what astronomers playfully call galactic pinball, where countless stellar flybys over billions of years have gradually altered its speed and direction. This pinball effect makes it impossible to backtrace 3I-ATLAS to a specific parent star. Even tiny uncertainties in present-day measurements balloon exponentially when projected backward over cosmic timescales. After billions of years and thousands of stellar encounters, the original trajectory has been completely scrambled. We can determine general galactic neighborhoods and stellar populations, but not individual stellar systems. Think of 3I-ATLAS as a message in a bottle that's been floating in galactic currents for eons. The bottle itself, the object's structure and composition, carries information about where it was originally cast into the cosmic ocean. But the current location where we found it tells us little about its specific origin point. The thick disk origin scenario paints a fascinating picture of deep time. This object may have formed when our galaxy was young and violent, when star formation rates were higher and stellar encounters more frequent. It may have witnessed the formation and destruction of countless stellar systems, the birth and death of stars whose light has long since faded from the cosmic scene. If 3I-ATLAS is indeed billions of years old, potentially older than our entire solar system, then it represents a kind of geological survey of galactic evolution. Its ice composition encodes the chemical conditions that existed in some distant stellar nursery when the universe was perhaps half its current age. We're essentially conducting archaeological chemistry across both space and time. NASA's preliminary assessments, based on Hubble Space Telescope observations and orbital dynamics, support the ancient wanderer hypothesis. The object's behavior appears consistent with a natural comet that has been adrift in interstellar space for billions of years, slowly accumulating cosmic ray damage and gravitational perturbations that explain its current trajectory and activity level. This timeline also helps explain some of 3I-ATLAS's unusual characteristics. A comet that has spent billions of years in the cold of interstellar space would develop a thick, insulating crust of non-volatile materials. When finally heated by a new star, our Sun, this ancient ice would begin sublimating from a surface that hasn't seen sunshine for geological epochs. The high activity level observed in 3I-ATLAS, with roughly 20% of its surface actively venting gas and dust, supports this first sunrise in eons scenario. The sublimating ice is fresh and enthusiastic, having been locked away beneath a protective crust throughout its interstellar journey. The directional information provides one final piece of the puzzle. While we can't determine 3I-ATLAS's specific stellar origin, its current velocity vector suggests it originated somewhere in the galaxy's inner regions before being scattered outward by gravitational encounters. This is consistent with the thick disk population, which tends to have more eccentric orbits and higher velocity dispersions than the younger thin disk stars. The chemical analysis that will occur during perihelion represents our best opportunity to test the ancient origin hypothesis. If 3I-ATLAS indeed formed around a metal-poor star billions of years ago, its volatile inventory should tell that story in precise detail. Water should dominate. Carbon-bearing molecules should be scarce. Isotopic ratios should reflect the galactic chemical conditions that existed in the deep past. This isn't just abstract cosmic archaeology. Understanding the composition and evolution of the galactic thick disk helps us piece together the history of star formation, chemical enrichment, and planetary system formation across cosmic time. 3I-ATLAS may be our first direct sample of matter from the galaxy's ancient neighborhoods, a time capsule that has traveled billions of light years and billions of years to end up in our telescopes. As we await the perihelion chemistry results, one thing remains certain: whether 3I-ATLAS proves to be a natural ancient wanderer or something more exotic, it carries information about cosmic processes that operated long before our Sun ignited and our Earth formed. Part 5. An Ice Heart Beneath a Dusty Hood. The first definitive image arrived on July 21, 2025, captured by the Hubble Space Telescope as it tracked 3I-ATLAS across the star field. What emerged from the data processing was a perfect teardrop of light, a bright nucleus surrounded by a fuzzy coma of dust and gas, with a subtle tail streaming away from the sun's direction. The image itself tells a story of controlled violence. As 3I-ATLAS approached our sun from a distance of roughly 3 astronomical units, 3 times Earth's orbital distance, solar radiation began heating its surface for the first time in potentially billions of years. Ancient ices, locked beneath a protective crust formed during eons of cosmic ray bombardment, started to sublimate. Water vapor carried dust particles away from the nucleus, creating the characteristic coma that defines cometary behavior. What makes this image particularly compelling is its ordinariness. The dust coma looked exactly like what astronomers expect from a natural comet at that distance from the Sunday. No exotic structures, no geometric patterns, no signs of artificial construction, just the gentle hiss of ice turning to vapor and carrying rocky debris along for the ride, what we might call the universe's most elegant steam engine. The tracking method used by Hubble reveals important details about the observation. Because the telescope followed 3I-ATLAS's motion across the sky, background stars appear as streaks in the final image. This technique, while making for dramatic visuals, also enables precise measurements of the coma's structure and the nucleus's size. Those size measurements proved crucial for understanding the energetics of what we were observing. The nucleus of 3I-ATLAS measures less than 5.6 kilometers in diameter and possibly just a few hundred meters across. This relatively small size creates interesting constraints on the object's origin story. Ejecting a multi-kilometer object from another star system requires enormous energies, the kind generated by close encounters with giant planets or stellar collisions. A smaller object, by contrast, could be launched into interstellar space by more modest gravitational disturbances. But there's a flip side to the size constraint. A sub-kilometer nucleus that produces such a prominent coma suggests an unusually active surface. Current estimates indicate that roughly 20% of 3I-ATLAS's surface is actively sublimating ice and venting gas, 4 times the typical activity level for solar system comets. This hyperactivity could result from fresh ices exposed by recent impacts, fracturing during the interstellar journey, or simply the enthusiastic response of ancient ice finally experiencing sunshine after eons of cold storage. The coma's morphology provides additional clues about the nucleus's structure and rotation. Subtle asymmetries in the dust distribution suggest that sublimation isn't uniform across the surface. Certain regions or features may be more active than others. This kind of patchy activity is common in comets and typically results from compositional variations, topographical features that focus solar heating, or seasonal effects as different hemispheres become exposed to sunlight. What we haven't yet observed is the development of a classic cometary tail. While the current coma shows dust streaming generally away from the sun, the dramatic, stretched tail structure that characterizes comets closer to perihelion has not yet formed. This timing makes sense. 3I-ATLAS is still relatively far from the sun, and tail formation typically accelerates dramatically as comets approach within 2 astronomical units of our star. The observational constraints add urgency to the scientific program. As 3I-ATLAS continues its approach toward perihelion in late October, its elongation angle, the apparent separation between the comet and sun as seen from Earth, will steadily decrease. By late October and early November, the object will disappear into solar glare, making direct observation impossible during the critical perihelion passage. This timing creates both challenges and opportunities. The solar conjunction period means we won't be able to directly observe 3I-ATLAS's behavior at closest approach, when heating effects reach their maximum and any artificial propulsion systems would most likely activate. But it also means that post-perihelion observations in early December will provide a clean test of theoretical predictions. If the object emerges from conjunction with a trajectory that precisely matches natural outgassing models, the case for artificial origin becomes much weaker. The dust grain analysis remains one of the most promising avenues for determining composition and origin. different stellar environments produce different types of dust. Variations in grain size, mineral composition, and crystalline structure that encode information about formation conditions. Hubble's high-resolution imaging can measure these properties by analyzing how the coma scatters sunlight at different wavelengths. Current data suggest grain sizes consistent with typical cometary material, particles ranging from submicron dust to millimeter-sized chunks, all held together by sublimating water ice. The absence of unusual grain properties or exotic compositions supports the natural origin hypothesis, though more detailed spectroscopic analysis will be required for definitive conclusions. The rotation state of the nucleus provides another diagnostic tool. Most comets exhibit complex rotation patterns that result from uneven outgassing forces. The same rocket effect that creates small trajectory changes also applies torques that alter spin rates and orientations. If 3I-ATLAS shows evidence of complex rotation, it would further support the case for natural cometary behavior. Perhaps most importantly, the dust observations establish a baseline for interpreting chemical measurements. The presence of a normal-looking dust coma means that any unusual chemical signatures can be attributed to genuine compositional differences rather than exotic physical processes. We're looking at a real comet that happens to come from another star system, not some fundamentally different class of object. As autumn approaches, and 3I-ATLAS continues its relentless approach toward perihelion, the dust coma will continue evolving. The teardrop shape will likely stretch into a more pronounced tail. Activity levels may increase as fresh ice deposits become exposed. New jets or outbursts could reveal subsurface structures or compositional variations. Each of these changes will be monitored and measured, building a comprehensive picture of how interstellar comets respond to solar heating. The dust may look ordinary now, but it carries extraordinary information about conditions in alien stellar systems, information that will help us understand not just where 3I-ATLAS came from, but how planetary systems form and evolve throughout our galaxy. Part 6. The Water Puzzle. Why 3 breathes differently? Something was wrong with the chemistry. By late July 2025, as 3I-ATLAS continued its approach toward our Sun, the Swift Space Telescope began detecting strong hydroxyl signatures, the telltale spectral fingerprints of water vapor sublimating from the comet's nucleus. This wasn't unexpected. Water ice is the most common volatile in solar system comets, and finding it in an interstellar visitor should have been routine. What puzzled astronomers was not what they found, but what they didn't find. Despite careful searches across multiple wavelengths and observation campaigns, no one could detect cyanogen, CN, in 3I-ATLAS's coma. This absence was deeply strange. Cyanogen typically appears early and prominently in cometary spectra, often before water vapor becomes detectable. It's one of the first molecules to sublimate as comets approach the Sun, making its absence in a water-active comet highly unusual. The implications of this chemical fingerprint extend far beyond simple composition. In our solar system, comets show a characteristic ratio of water to carbon-bearing molecules that reflects the conditions under which they formed. The water-rich, carbon-poor signature of 3I-ATLAS suggests formation in a very different environment, one where water ice was abundant but carbon-bearing compounds were scarce. This chemistry tells a story about stellar neighborhoods and galactic evolution. Stars that formed early in our galaxy's history did so from gas clouds that contained far fewer heavy elements than the enriched material available today. Carbon, nitrogen, and other complex molecules were rare commodities in the ancient universe, while hydrogen and oxygen, the ingredients for water, were relatively abundant. A comet that formed around such an ancient metal-poor star would naturally exhibit exactly the water-heavy, carbon-light composition observed in 3I-ATLAS. The distance at which this water activity became detectable adds another layer to the mystery. Swift spotted strong hydroxyl signatures when 3I-ATLAS was still roughly 3.5 astronomical units from the Sun, surprisingly far out for robust water sublimation. Most solar system comets don't become strongly water active until they pass within about 3 astronomical units of our star. This early activity suggests either an unusually volatile surface composition or structural features that enhance solar heating efficiency. Current estimates indicate that approximately 20% of 3I-ATLAS's surface is actively sublimating, compared to the 5% typical for solar system comets. This hyperactivity could result from several factors. Fresh ice exposures created by micrometeorite impacts during the interstellar journey. Fracturing caused by thermal stresses as the object transitions from the cold of space to solar heating. Or simply the enthusiastic response of ice that hasn't seen starlight for billions of years. The absence of cyanogen remains the central puzzle. Several alternative explanations remain possible, and scientists are being careful not to overinterpret preliminary data. Dust reddening, the same effect that makes Earth's sunsets appear red, could be hiding weak CN emission lines by preferentially absorbing blue light. Viewing geometry might be unfavorable for detecting CN jets if they're oriented away from Earth. Instrumental sensitivity limitations could mean the signals are there but below detection thresholds. More tantalizingly, the chemistry could evolve as 3I-ATLAS approaches perihelion. Many comets show changing volatile ratios as heating increases and different ice reservoirs become exposed. Carbon dioxide and carbon monoxide typically require more heating than water to sublimate efficiently. If 3I-ATLAS contains these molecules in subsurface layers, they might emerge dramatically during the October perihelion passage, transforming the apparent composition from water-dominated to something more familiar. The spectroscopic program designed to monitor this evolution represents one of the most comprehensive chemical analyses ever attempted on an interstellar object. Multiple telescopes are tracking 3I-ATLAS across different wavelengths, looking for trace signatures of dozens of different molecules. The inventory includes not just major volatiles like water and carbon monoxide, but also organic compounds, metallic species, and isotopic variations that could reveal formation conditions. Isotopic ratios deserve particular attention. Different stellar environments produce different ratios of isotopes, variations in atomic mass for the same element that encode information about nuclear processes in the parent star. The deuterium to hydrogen ratio in water, for example, varies significantly between different formation environments. If 3I-ATLAS shows isotopic signatures that differ from solar system values, it would provide definitive proof of extrasolar origin and clues about the type of star around which it formed. The water activity also enables studies of non-gravitational forces, the subtle rocket effects created when sublimating gas pushes against the comet nucleus. These forces are tiny but measurable, and they create characteristic signatures in the object's trajectory that can be distinguished from pure gravitational motion. Natural comets show non-gravitational accelerations that correlate precisely with observed outgassing activity. Artificial objects might show very different patterns. What could fool the chemical analysis? Dust contamination that masks weak spectral lines. Seasonal effects, if the active regions are concentrated in specific hemispheres. Subsurface layering that creates temporal evolution in the volatile inventory. Interaction with the solar wind that alters the chemistry of the coma itself. The upcoming perihelion passage represents the critical test for all chemical models. As 3I-ATLAS reaches its closest approach to the Sun in late October, heating effects will reach their maximum. Any subsurface volatiles will be exposed. Hidden ice reservoirs will begin sublimating. The true chemical inventory of this interstellar visitor will finally be revealed. But there's a catch. Perihelion occurs during solar conjunction, when 3I-ATLAS passes behind the Sun, as seen from Earth. Direct observation during this critical period will be impossible. The chemical evolution that astronomers most want to study will occur hidden from view, like a magician's trick performed behind a curtain. This timing constraint makes the post-perihelion emergence in early December absolutely crucial. When 3I-ATLAS reappears from behind the Sun, Its chemical signature should tell the complete story of its encounter with intense solar heating. If it's a natural comet from an ancient, metal-poor stellar environment, the water-heavy, carbon-poor signature should persist or even strengthen. If hidden volatiles exist, they should finally emerge in detectable quantities. The water puzzle may ultimately prove to be the smoking gun that reveals 3I-ATLAS's true nature, not through what it contains, but through what it conspicuously lacks. And when those absences finally give way to the full chemical symphony of an awakened interstellar comet. Part 7. The Silent Radio. Listening for a signal that never came in the quiet hours before dawn, when terrestrial radio interference fades to whispers. Massive dish antennas across the globe turn their electronic ears toward a point of light racing through the constellation Sagittarius. They listen with infinite patience for a signal that logic says shouldn't exist, but that human curiosity demands we seek anyway. The search for extraterrestrial intelligence has maintained an uneasy relationship with interstellar objects since the arrival of Oumuamua in 2017. While most astronomers focused on natural explanations for that enigmatic visitor's unusual properties, SETI researchers quietly added it to their target lists. The logic was simple. If an advanced civilization ever sent a probe to survey our solar system, it would likely arrive on an interstellar trajectory, disguised as, or perhaps actually constructed from, a natural object like an asteroid or comet. 3I-ATLAS presents an even more compelling target for radio surveillance. Unlike Oumuamua, which was discovered only after perihelion and studied for mere weeks, 3I-ATLAS provides months of advance, warning, and optimal observing geometry. If this wanderer carries any artificial intelligence, any monitoring equipment, or any communication systems, the extended observation window offers our best chance yet to detect the electromagnetic signatures of technology operating in our cosmic neighborhood. The technical challenges of listening for interstellar signals are formidable. Imagine trying to detect a cell phone conversation from 200 million miles away, while both the transmitter and receiver are moving at tens of kilometers per second through space, filled with natural radio noise from lightning, solar activity, and cosmic phenomena. Any artificial signal would need to overcome this background static while compensating for the rapid Doppler shifts caused by 3I-ATLAS's hyperbolic trajectory. The Doppler effect provides both obstacle and opportunity for SETI searches. As 3I-ATLAS races through our solar system at 60 kilometers per second, any radio transmission would experience continuous frequency drift, the cosmic equivalent of a passing ambulance siren changing pitch. Traditional SETI searches look for stable, narrowband signals that stand out against the broadband noise of natural phenomena. Signals from 3I-ATLAS would require specialized software capable of tracking rapid frequency changes while maintaining the sensitivity necessary to detect weak transmissions across interplanetary distances. The Green Bank Telescope in West Virginia, one of the world's largest steerable radio dishes, has pointed its 100-meter aperture toward 3I-ATLAS during several extended observation sessions. The facility's location in the National Radio Quiet Zone, a region where terrestrial radio transmissions are strictly regulated, provides optimal conditions for detecting faint signals from space. Green Bank's receivers can monitor hundreds of millions of frequency channels simultaneously, searching for the telltale patterns that might indicate artificial origin. The Allen Telescope Array in California contributes its own unique capabilities to the search. This facility consists of 42 individual dishes that can be electronically combined to create a single, highly sensitive instrument. The array's design allows it to monitor multiple targets simultaneously while maintaining continuous coverage of 3I-ATLAS throughout its visible passage across Earth's sky. The distributed architecture also provides built-in verification. Any genuine signal should appear in multiple dishes with the precise timing delays expected from the array geometry. Citizen scientists have joined the search through distributed computing projects that analyze recorded radio data on millions of volunteer computers worldwide. The SETI-at-Home successor projects can process vast quantities of radio observations, hunting for patterns that might escape automated detection algorithms. Amateur radio operators have also contributed by monitoring 3I-ATLAS with their own equipment, creating a global network of independent observers who could potentially detect signals missed by professional facilities. The search protocols follow rigorous scientific standards designed to minimize false alarms while maximizing detection sensitivity. Any candidate signal must appear consistently across multiple observation sessions, show the expected Doppler drift pattern for 3I-ATLAS's known trajectory, and be independently confirmed by at least 2 separate observatories. These requirements eliminate most terrestrial interference while ensuring that any positive detection would meet the extraordinary evidence standards required for extraordinary claims. Previous SETI observations of interstellar objects have yielded only null results, but these negative findings carry their own scientific value. The absence of detectable signals places upper limits on the power output of any hypothetical transmitter aboard 3I-ATLAS. Current sensitivity levels rule out continuous transmissions stronger than a few kilowatts, roughly equivalent to a terrestrial radio station, operating in the frequency ranges monitored by SETI facilities. These power limits assume omnidirectional broadcasting, where radio energy spreads uniformly in all directions through space. Highly directional transmissions, focused like a laser beam towards specific targets, could operate at much lower power levels while remaining detectable to Earth-based receivers. However, such focused signals would require precise pointing accuracy and advanced knowledge of Earth's position, capabilities that would themselves constitute evidence of sophisticated intelligence. The monitoring campaign has revealed the universe's natural radio environment around 3I-ATLAS's position. Solar wind interactions, planetary magnetospheres, and cosmic ray particles all generate radio noise that must be carefully filtered from observations. Jupiter, in particular, produces intense radio bursts that can overwhelm sensitive receivers when the giant planet appears near the target direction. These natural phenomena remind us that space is far from electromagnetically quiet, creating a complex background against which any artificial signals must compete. The silence from 3I-ATLAS strengthens the case for natural origin while demonstrating the scientific rigor applied to testing extraordinary hypotheses. Just as visible light observations revealed ordinary cometary activity rather than exotic materials, radio observations show a cosmos populated by natural phenomena rather than technological artifacts. This null result aligns with theoretical expectations. If interstellar probes were common, we might expect to detect multiple examples rather than ambiguous single cases. Yet the search continues throughout 3I-ATLAS's solar encounter. Perihelion passage might trigger enhanced activity if the object contains any dormant systems activated by solar heating. The post-perihelion emergence window in December provides one final opportunity to detect signals as 3I-ATLAS recedes toward interstellar space. If any intelligence aboard this wanderer plans to phone home, the end of its solar system visit would represent a logical time for transmission. The coordination between optical and radio observations creates synergies that enhance both detection strategies. Visible light monitoring reveals periods of enhanced activity when outgassing reaches peak intensity, precisely when any embedded systems might draw power from solar panels or radioisotope generators. Radio observations during these active periods could detect the electromagnetic signatures of equipment responding to changing thermal or power conditions. The broader implications of SETI monitoring extend beyond 3I-ATLAS itself. Each interstellar visitor provides an opportunity to refine detection techniques and establish protocols for rapid response radio surveillance of future objects. As interstellar discoveries become more frequent, SETI facilities are developing automated systems that can immediately begin monitoring newly detected objects without waiting for human intervention. The public engagement aspect of Radio SETI adds another dimension to the search. Unlike the technical complexities of spectroscopic analysis or astrometric precision, the concept of listening for radio signals resonates intuitively with general audiences. The romantic notion of cosmic messages traveling across the void captures imaginations and generates support for both SETI research and astronomical surveys that discover interstellar objects. Educational opportunities abound in explaining how radio astronomy works, why Doppler shifts matter, and what kinds of signals might indicate artificial origin. The search for signals from 3I-ATLAS serves as a gateway for discussing broader questions about intelligence in the universe, the likelihood of technological civilizations, and the methods scientists use to test speculative hypotheses. As 3I-ATLAS continues its silent passage through our solar system, the radio telescopes maintain their patient vigil. They listen to a universe that speaks primarily in the random static of natural phenomena, searching for the structured patterns that would indicate purposeful transmission. So far, that search has yielded only the whispers of cosmic wind and the occasional burst from distant galaxies. The silence itself tells a story, not of disappointment, but of scientific methodology applied to extraordinary questions. We listened with our best instruments, searched with our most sophisticated algorithms, and heard the universe as it actually is, rather than as our imaginations might prefer it to be. In that discipline lies the true success of the radio search, not in detecting alien signals, but in demonstrating our commitment to evidence over speculation. Part 8. Oumuamua, Borisov, Atlas. 3 visitors, 3 stories. To understand what makes 3I-ATLAS special, we need to examine it against the only context we have, the 2 previous interstellar visitors that have graced our solar system in the past decade. Each object tells a different story about the universe beyond our cosmic neighborhood, and together they're beginning to sketch the outlines of a population we never knew existed. 1I, Oumuamua, arrived first. In October 2017, like a cosmic calling card from an unknown civilization, this elongated, tumbling object defied easy categorization from the moment of its discovery. Roughly 400 meters long and perhaps 40 meters wide, it resembled an interstellar cigar more than any comet or asteroid from our solar system. Most puzzling of all, it showed no visible coma or tail, despite passing well within the orbit of Venus. The absence of obvious cometary activity initially led astronomers to classify Oumuamua as an asteroid, a chunk of rock somehow ejected from another star system. But as precise measurements of its trajectory accumulated, a small but undeniable anomaly emerged. The object was accelerating away from the Sun, slightly faster than gravity alone could explain. This non-gravitational acceleration was tiny, about the force you'd feel from a gentle breeze, but it was real and measurable. The discovery of this anomalous acceleration sparked intense debate. Natural explanations focused on subtle outgassing that was somehow invisible to telescopes, perhaps hydrogen gas produced by cosmic ray bombardment, or water vapor venting from a surface too small or too quickly changing to detect. More exotic theories suggested everything from solar sails to alien probes, turning Oumuamua into a cultural phenomenon that transcended astronomy. The truth about Oumuamua remains elusive. Late discovery meant limited observation time, and the object's faintness restricted detailed chemical analysis. By the time astronomers realized what they were looking at, it was already racing back toward interstellar space. Oumuamua became the interstellar visitor that got away, a tantalizing mystery that raised more questions than it answered. 2Y, Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, told a completely different story. This object behaved exactly like astronomers expected an interstellar comet to behave. It developed a prominent coma and tail as it approached the Sunday. Spectroscopic analysis revealed water vapor, carbon monoxide, and dust compositions that fell well within the range of solar system comets. Even its nucleus size, roughly 1 kilometer in diameter, matched theoretical predictions for objects ejected from other planetary systems. If Oumuamua was the mysterious stranger who left before anyone could get a good look, Borisov was the polite visitor who followed all the rules. Its chemistry suggested formation in a planetary system not too different from our own. Its behavior matched textbook cometry physics. Its trajectory showed the expected non-gravitational accelerations that correlated perfectly with observed outgassing activity. Borisov's normalcy was almost disappointing. After the excitement generated by Oumuamua's anomalies, astronomers found themselves studying what appeared to be a perfectly ordinary comet that happened to come from another star. The object confirmed that interstellar comets existed and could be studied with conventional techniques, but it didn't reveal any exotic chemistry or surprising behavior. Now comes 3I-ATLAS, the third act in this unfolding cosmic drama. Like Borisov, it shows clear cometary activity with a dust coma and evidence of water sublimation. Like Oumuamua, it presents puzzling characteristics that don't quite fit standard models. The early water activity, the absence of cyanogen, the unusual orbital geometry, each feature falls within the realm of the possible, but at the edge of the probable. What emerges from comparing these three visitors is evidence of genuine diversity in the interstellar population. They're not all variations on a single theme. Oumuamua might represent a class of small, rocky objects with minimal volatile content. Borisov exemplifies typical comets ejected from planetary systems similar to our own. Atlas could be showing us ancient comets from the galaxy's early epochs, when stellar chemistry was very different from today's enriched environment. The observational lessons learned from each discovery have been crucial for studying the next. Oumuamua taught astronomers the importance of early detection and rapid response. Borisov demonstrated that comprehensive spectroscopic analysis was possible with sufficient observation time. Atlas benefits from both lessons. Early discovery provides ample observation windows, while improved detection capabilities enable detailed chemistry from the start. The discovery cadence itself tells an important story. 3 interstellar objects in 8 years, 2017, 2019, 2025, suggests that such visitors may be more common than previously suspected. Current surveys like ATLAS, Catalina, and the upcoming Rubin Observatory may detect interstellar objects on a regular basis, transforming them from cosmic rarities into routine subjects for study. Each object also represents a different observational success story. Oumuamua was found by the Pan-STARRS survey during routine asteroid hunting. Borisov was discovered by a dedicated amateur astronomer using a homemade telescope. Atlas was spotted by a professional survey designed specifically to find potentially hazardous asteroids. This diversity of discovery methods suggests that improved surveys will dramatically increase the detection rate. The population statistics emerging from 3 data points remain highly uncertain, but they provide the first constraints on how many interstellar objects pass through our solar system undetected. Current estimates suggest that several such visitors transit our neighborhood each year, with most going unnoticed due to their faintness or unfavorable observation geometry. What would a 4th interstellar visitor tell us? A larger sample size would enable statistical analysis of properties like size distribution, composition ranges, and trajectory characteristics. Pattern recognition becomes possible with more data points. The distinction between rare coincidences and systematic properties becomes clearer. The next generation of survey telescopes promises to transform interstellar object science from anecdotal case studies to systematic population analysis. The Rubin Observatory, scheduled to begin operations soon, will monitor the entire visible sky every few nights with sensitivity far exceeding current capabilities. JWST can perform detailed spectroscopic analysis on objects that would have been too faint for previous instruments. These improvements mean that 3I-ATLAS may represent the last interstellar visitor studied in isolation. Future discoveries may come in groups, enabling comparative analysis that reveals patterns invisible in individual objects. We're transitioning from the era of interstellar visitors as cosmic curiosities to their recognition as a regular component of solar system science. The three visitors we've studied so far, Oumuamua the mysterious, Borisov the conventional, and Atlas the ancient, have established that interstellar space contains a diverse population of objects with varied compositions, structures, and histories. Each visitor carries information about different stellar environments, different epochs of galactic evolution, and different mechanisms for ejecting material between star systems. As we await the perihelion passage of 3I-ATLAS and prepare for the inevitable discovery of 4I, 5I, and beyond, we're beginning to appreciate that these visitors offer our best opportunity to study the products of alien planetary systems without leaving our own solar neighborhood. Part 9. How do stars throw out comets? The natural origin pathway. To understand how 3I-ATLAS might have ended up in our solar system, we need to examine the violent processes that fling objects between star systems. The galaxy is not a peaceful place. Stellar systems constantly jostle and perturb each other through gravitational interactions that can eject material across interstellar distances. Understanding these mechanisms provides the foundation for evaluating whether 3I-ATLAS represents a natural exile from another world. The most efficient comet ejection factory operates in the outer regions of planetary systems, the cosmic equivalent of our Kuiper Belt and Oort cloud. These distant realms contain vast populations of icy bodies weakly bound to their parent stars. A gravitational nudge that would barely affect an inner planet can send these outer objects careening toward interstellar space at hyperbolic velocities. Giant planet migration provides one of the most powerful ejection mechanisms. As massive worlds like Jupiter and Saturn settle into their final orbits, they gravitationally scatter smaller bodies like cosmic billiard balls. Computer simulations suggest that our own solar system ejected thousands of objects for every one that remained in stable orbits. The same process operating around other stars would populate interstellar space with a steady stream of icy debris. The timing of these ejections varies dramatically depending on system architecture and evolution. Early ejection occurs during the first few 100 million years after planetary formation, when orbits are still settling and migration rates are highest. Late ejection can happen billions of years later, when passing stars perturb the outer comet clouds, or when binary star companions destabilize distant orbits. Stellar encounters provide another major source of interstellar comets. When two star systems pass within a few light years of each other, a common occurrence in the crowded stellar neighborhoods of our galaxy, their gravitational fields can strip comets from each other's outer regions. These encounters are particularly effective in dense stellar environments like globular clusters or the central regions of galaxies. The speeds observed in interstellar visitors, like 3I-ATLAS, result from billions of years of such gravitational encounters. Each stellar flyby adds or subtracts velocity in a process astronomers call galactic pinball. Over cosmic timescales, these accumulated perturbations can accelerate objects to the 60+ kilometers per second observed in our interstellar visitors. This prolonged acceleration explains why we can't trace 3I-ATLAS back to a specific parent star. Even tiny uncertainties in present-day measurements balloon exponentially when projected backward through billions of years of chaotic gravitational encounters. The object's current trajectory tells us about its general galactic neighborhood and stellar population, but not its specific stellar birthplace. The composition of 3I-ATLAS provides clues about the type of system that originally hosted it. The water-rich, carbon-poor chemistry suggests formation around an ancient metal-poor star, the kind that dominated galactic star formation in earlier epochs. Such stars had access to hydrogen and oxygen for making water ice, but lacked the heavier elements needed for complex carbon compounds. This chemical fingerprint supports the natural ejection hypothesis in multiple ways. First, it matches theoretical predictions for comets formed in low metallicity environments. Second, it's consistent with the thick disk origin suggested by 3I-ATLAS's kinematics. Third, It differs significantly from solar system compositions in exactly the ways expected for objects from older stellar populations. The size distribution of ejected objects depends on the specific mechanisms involved. Giant planets scattering efficiently ejects smaller bodies, but struggles with larger ones. The energy requirements scale with mass, making it progressively more difficult to fling massive objects into interstellar space. This creates a natural bias towards smaller comets like 3I-ATLAS, which measures less than a few kilometers across. Selection effects complicate our understanding of the true interstellar population. We only detect the objects that happen to pass close enough to Earth and become bright enough for our telescopes. The vast majority of interstellar visitors probably go unnoticed, either because they follow trajectories that don't bring them near our planet, or because they're too small and faint to detect. Current estimates suggest that several interstellar objects traverse our solar system each year, with detection rates limited by survey sensitivity and coverage. The 3 confirmed visitors discovered since 2017 probably represent a tiny fraction of the actual population passing through our cosmic neighborhood. The natural ejection process also explains the diverse properties observed in interstellar visitors. Oumuamua's small size and apparent lack of volatiles could result from formation closer to its parent star, where radiation pressure removed lighter elements. Borisov's normal cometary composition suggests origin in a system similar to our own. Atlas's ancient chemistry reflects formation in the galaxy's earlier epochs. This diversity argues against artificial origin theories that would require a single type of technology or materials science. Natural processes operating across different stellar environments and epochs would naturally produce the range of compositions and structures observed in interstellar visitors. The ejection rate from individual stellar systems depends on architecture, age, and environment. Young systems with actively migrating giant planets produce higher ejection rates than mature systems with settled orbits. Systems in dense stellar clusters experience more frequent encounters that strip away outer comet populations. Binary star systems have additional destabilization mechanisms that don't exist around single stars like our Sunday. Population synthesis models that incorporate these various ejection mechanisms predict interstellar object encounter rates consistent with current observations. The models also predict that improved surveys should dramatically increase detection rates, potentially finding dozens or hundreds of interstellar visitors in the coming decade. Testing the natural origin hypothesis requires comparing predicted and observed properties across multiple objects. Chemical compositions should reflect the stellar metallicity distributions in different galactic populations. Size distributions should match theoretical ejection efficiency curves. Trajectory statistics should align with models of galactic dynamics and stellar encounters. As 3I-ATLAS approaches perihelion and reveals its complete chemical inventory, these tests become increasingly precise. A natural origin predicts specific volatile ratios, isotopic signatures, and outgassing behaviors that can be compared directly with observations. Deviations from these predictions would challenge our understanding of either the ejection process or the object's true nature. The broader implications extend beyond individual objects to our understanding of planetary system formation and evolution throughout the galaxy. Interstellar comets provide direct samples of materials from alien worlds, chemical messengers that carry information across the vast distances that separate star systems. Part 10. The Alien Probe Hypothesis, a Darker Possibility. The mathematics of suspicion began with orbital geometry. When Abraham Loeb and his colleagues Sean Hibbard and Adam Crowell ran the numbers on 3I-ATLAS's trajectory, they found patterns that made them pause. The object's path didn't just skim our solar system's ecliptic plane, it choreographed a cosmic dance that brought it near multiple planetary orbits with what seemed like deliberate precision. Their R-exiv preprint, submitted in the heat of discovery excitement, outlined a hypothesis that challenged the astronomical mainstream. What if 3I-ATLAS wasn't a natural comet at all, but rather an artificial probe designed to study our solar system? The paper reads like a technical thriller, methodically building a case for engineered origin through orbital mechanics, trajectory timing, and strategic positioning. The ecliptic skimming geometry forms the cornerstone of their argument. Most randomly oriented interstellar trajectories would approach our solar system at steep angles, diving through the planetary plane rather than following it. The authors calculate that trajectories within 5 degrees of the ecliptic occur naturally in roughly 1 out of 500 encounters, possible but statistically suspicious. More intriguing is the multi-planetary proximity. 3I-ATLAS's path carries it through the gravitational neighborhoods of Venus, Earth, Mars, and Jupiter in sequence. Not close encounters that would significantly alter its trajectory, but passages that would enable remote sensing of each world's electromagnetic environment, atmospheric composition, and magnetic field characteristics. It's the kind of survey pattern a systematic exploration program might design. The timing adds another layer of apparent intentionality. 3I-ATLAS reaches perihelion when our Sun lies directly between the object and Earth, a configuration called superior conjunction. This geometry would provide perfect cover for any propulsion system activations, hiding potential engine burns behind the Sun's overwhelming brightness and radio interference. Loeb and his colleagues even calculated hypothetical arrival windows. If 3I-ATLAS were to perform powered maneuvers during perihelion, using what engineers call a reverse Oberth effect to break into our solar system, it could theoretically achieve Earth encounter by early 2026, or Jupiter encounter by 2028. These remain purely speculative scenarios, but they demonstrate the mathematical feasibility of the probe hypothesis. The early no-coma observations initially strengthened the artificial origin case. When first discovered, 3I-ATLAS showed no obvious signs of cometary activity, no dust tail, no gas emissions, no evidence of sublimating ice. This absence of volatiles seemed inconsistent with natural comet behavior and more compatible with an artificial object constructed from non-volatile materials. However, this pillar of the probe hypothesis has since crumbled. Hubble Space Telescope images clearly show a dust coma streaming from 3I-ATLAS's nucleus. Swift observations detect strong water vapor signatures. The object is definitely outgassing like a natural comet, demonstrating genuine volatile content and thermal response to solar heating. The size constraints add both support and challenge to the artificial hypothesis. If 3I-ATLAS measures several kilometers across, as some early estimates suggested, then ejecting it from another star system would require enormous energies, the kind generated by close encounters with giant planets or stellar collisions. An artificial origin might actually be more plausible than natural ejection for very large objects, but subsequent observations suggest a much smaller nucleus, possibly just hundreds of meters across. Objects this size can be ejected naturally through relatively modest gravitational perturbations, making artificial origin less necessary to explain its presence in our solar system. The scientific community's response to the probe hypothesis has been measured but skeptical. Extraordinary claims require extraordinary evidence, and the patterns cited by Loeb and colleagues, while statistically interesting, don't rise to the level of proof. Coincidences do occur in nature, especially when viewed through the lens of selection effects and observational biases. More critically, the hypothesis makes testable predictions about 3I-ATLAS's behavior that can be evaluated through ongoing observations. An artificial probe should show trajectory modifications that can't be explained by natural outgassing, sudden velocity changes, course corrections during solar conjunction, accelerations that persist after cometary activity ceases. Natural comets, by contrast, follow predictable patterns of non-gravitational acceleration that correlate precisely with observed outgassing activity. The rocket effect of sublimating gas creates small but measurable changes in trajectory that match detailed physical models. Any deviations from these predictions would constitute genuine evidence for artificial origin. Radio observations provide another test of the probe hypothesis. Artificial objects might emit narrowband signals, either for communication purposes or as byproducts of electronic systems. SETI-style monitoring during 3I-ATLAS's approach has detected no obvious artificial signals, though the search continues with increasing sensitivity as the object approaches perihelion. Radar observations could potentially reveal structural details inconsistent with natural formation. A coherent, geometric radar signature would suggest artificial construction rather than the chaotic internal structure expected from gravitational accretion. However, 3I-ATLAS's distance and trajectory make detailed radar studies extremely challenging with current technology. The probe hypothesis also faces the challenge of technological plausibility. Any civilization capable of constructing interstellar probes would presumably have access to advanced materials and propulsion systems. Why would such a probe rely on gravity assists and orbital mechanics rather than direct propulsion? Why would it follow such an indirect route to study our planets? These questions don't definitively rule out artificial origin, but they highlight the assumptions embedded in the hypothesis. Perhaps advanced civilizations prefer subtle, long-duration studies over direct approach. Perhaps resource constraints make gravity assists preferable even for advanced technologies. Perhaps the apparent inefficiencies reflect design priorities we don't understand. The broader context of Loeb's advocacy for the artificial hypothesis cannot be ignored. As the author of Extraterrestrial, a popular book arguing for the alien probe interpretation of Oumuamua, Loeb has established himself as astronomy's most prominent advocate for considering artificial origins for anomalous objects. This background brings both expertise and potential bias to his analysis of 3I-ATLAS. Nevertheless, the scientific process requires taking such hypotheses seriously while demanding rigorous evidence. The probe hypothesis has generated specific, testable predictions about 3I-ATLAS's future behavior. Post-perihelion observations will either confirm natural cometary physics or reveal anomalies that challenge our understanding. As of late 2025, no verified, non-gravitational accelerations beyond those expected from cometary outgassing have been reported in mainstream astronomical channels. NASA's official assessments continue to classify 3I-ATLAS as a natural interstellar comet, but the observation campaign continues, and definitive conclusions await the critical perihelion passage and post-conjunction emergence. The probe hypothesis serves an important function regardless of its ultimate validity. It forces astronomers to consider alternative explanations for anomalous observations. It generates testable predictions that strengthen the scientific analysis. And it reminds us that in a universe containing billions of potentially habitable worlds, the possibility of artificial visitors cannot be dismissed without proper investigation. The next few months will determine whether 3I-ATLAS joins the ranks of natural interstellar comets or becomes the first confirmed artificial visitor to our solar system. Part 11. The breakup question. Could 3 shatter like other comets? There's something inherently fragile about a cosmic snowball that has wandered the galaxy for billions of years. 3I-ATLAS may appear solid and permanent in telescopic images, but it's essentially an ancient ice sculpture racing toward an encounter with stellar radiation that could tear it apart in a matter of hours. The question isn't whether this interstellar wanderer will survive its solar encounter intact, it's whether we'll be watching when it decides to shatter. Cometary fragmentation represents one of the most dramatic spectacles in solar system astronomy. When comet Shoemaker-Levy 9 broke apart before colliding with Jupiter in 1994, it created a string of fragments that became individual projectiles in a cosmic shooting gallery. Comet Atlas C 2019 L3 disintegrated in 2020 as it approached the Sun, transforming from a single object into a cloud of debris that gradually dispersed along its orbital path. Even the famous Comet Hale-Bopp showed signs of partial fragmentation during its 1,000 997 apparition, ejecting chunks of material that became temporary satellites orbiting the main nucleus. The physics behind cometary breakup involves a delicate balance between structural strength and internal pressure. As a comet approaches the Sun, solar heating penetrates into the nucleus and begins sublimating buried ice. This phase transition from solid to gas creates enormous pressure gradients within the interior. If the structural integrity of the nucleus cannot withstand these forces, cracks begin to propagate through the material. Once fracturing begins, it often accelerates rapidly as gas pressure finds new pathways to escape, ultimately splitting the nucleus into multiple fragments. 3I-ATLAS shows several characteristics that place it at risk for fragmentation. Its small size, estimated at no more than a few kilometers in diameter, means that even modest internal pressures could overcome the weak gravitational self-attraction holding the nucleus together. The approximately 20% active surface area suggests either unusually fresh ice deposits or a highly fractured structure that exposes internal materials to direct solar heating. Both scenarios create conditions favorable for catastrophic disruption. The early appearance of a dust coma at 3.5 astronomical units from the Sun indicates that volatile sublimation is already underway, despite the relatively modest solar heating at that distance. This premature activity could reflect the presence of highly volatile species like carbon monoxide or nitrogen that sublimate at very low temperatures. Alternatively, it might indicate a nucleus so thoroughly fractured that even water ice sublimates efficiently due to the enormous surface area available for heating. Hubble Space Telescope images already show subtle asymmetries in the coma structure that could represent the early stages of fragmentation. Jets and plumes extending from the nucleus often mark the locations where internal pressure has found pathways to the surface. If these vents continue growing under increasing solar heating, they could develop into full-scale fractures that split the nucleus apart. The teardrop-shaped coma visible in current images might evolve into the elongated debris train characteristic of a fragmenting comet. The timing of 3I-ATLAS's perihelion passage, occurring in late October when the object will be lost in solar glare, creates observational challenges for monitoring potential fragmentation events. The most dramatic breakup episodes typically occur during the hours or days surrounding closest solar approach, precisely when ground-based telescopes cannot observe the object. Space-based observatories like the Solar and Heliospheric Observatory, SOHO, can monitor objects very close to the Sun, but their relatively modest spatial resolution might miss the subtle early stages of fragmentation. The post-perihelion emergence window in early December will provide the crucial test. If 3I-ATLAS has survived its solar encounter intact, it should appear as a single, well-defined nucleus surrounded by a symmetric coma. Evidence of fragmentation would include multiple condensations along the orbital path, asymmetric brightness distributions, or unusual spectroscopic signatures from freshly exposed internal materials. The absence or presence of these features will definitively answer whether this ancient wanderer possessed the structural integrity to survive its first stellar encounter in billions of years. A fragmentation event would actually enhance the scientific return from 3I-ATLAS in several important ways. Breaking apart would expose internal layers that have remained hidden since the object's formation billions of years ago. These pristine materials could reveal chemical gradients or compositional stratification that encode the thermal history of the original protoplanetary disk. Different volatile species might be concentrated at different depths within the nucleus, creating a natural core sample that fragmentation would make accessible to spectroscopic analysis. Multiple fragments would also provide independent targets for detailed study. Each piece might show different activity levels, chemical compositions, or thermal properties depending on its origin within the original nucleus. This multiplicity would allow comparative analysis that could reveal structural details impossible to determine from a single intact object. The size distribution of fragments would constrain models of cometary internal structure and mechanical strength. Conversely, Survival of the perihelion passage would suggest that 3I-ATLAS possesses either a larger size than current estimates indicate or an unusually strong internal structure. A rocky core surrounded by a relatively thin ice mantle might provide the mechanical strength necessary to resist fragmentation pressures. Such a structure would imply formation in the inner regions of its original planetary system, where rocky materials could condense before being scattered outward by planetary migration or stellar encounters. The fragmentation question adds dramatic suspense to the ongoing observation campaign. Unlike the gradual revelation of chemical composition or the slow refinement of trajectory measurements, cometary breakup can occur suddenly and irreversibly. One day, 3I-ATLAS might appear normal in telescopic images. The next day, it could be an expanding cloud of debris racing away from the sunday. This uncertainty transforms each observation into a potential witness to cosmic catastrophe. The analogy of watching an ancient snowball in a cosmic oven captures both the beauty and fragility of the situation. 3I-ATLAS represents a frozen relic from the early galaxy, preserved in the cold depths of interstellar space for longer than our solar system has existed. Its encounter with solar radiation constitutes the first significant thermal stress this object has experienced in billions of years. Whether it possesses the strength to survive this trial by fire will reveal fundamental truths about its structure, composition, and history. Telescopes around the world maintain constant vigilance for signs of change in 3I-ATLAS's appearance. Automated monitoring systems can detect brightness variations, coma asymmetries, or the appearance of multiple condensations that might indicate fragmentation in progress. The global coordination required for this surveillance demonstrates the scientific importance placed on capturing any breakup event in real time. The broader implications extend beyond a single comet. Understanding the mechanical properties and fragmentation thresholds of interstellar objects provides insights into their formation environments, thermal histories, and the physical processes that have shaped them during billions of years of galactic wandering. Each survival or destruction event adds data points to models of cometary evolution and the population characteristics of interstellar debris. As 3I-ATLAS approaches its moment of truth, racing toward perihelion with the accumulated momentum of a billion-year journey, we can only wait and watch. The next few weeks will determine whether this messenger from another star system emerges intact from its solar trial or shatters into fragments that scatter like cosmic confetti across the inner solar system. Either outcome will advance our understanding, but only one will preserve this ancient traveler for future generations to study and admire. The tension builds with each passing day, each telescopic observation, each spectroscopic measurement that might be our last glimpse of 3I-ATLAS as a unified whole. In this cosmic game of chance, the house always wins, but sometimes, just sometimes, the ancient snowballs prove tougher than expected, surviving their stellar encounters to continue their eternal journey through the galaxy. Part 12. The Watchers. Telescopes racing against time. The clock is ticking with astronomical precision. As 3I-ATLAS continues its relentless approach toward perihelion, Earth's most sophisticated telescopes are orchestrating the most comprehensive study ever attempted of an interstellar visitor. But they're racing against geometry itself, the inevitable dance of orbits that will soon hide this cosmic mystery behind the overwhelming glare of our Sunday. The observation timeline reads like a countdown to scientific opportunity. From discovery in July through early October, 3I-ATLAS remains optimally positioned for detailed study. The object's elongation angle, its apparent separation from the Sun as seen from Earth, provides dark skies and extended observation windows. But as October progresses toward perihelion on the 29th and 30th, that angle steadily shrinks. By late October, 3I-ATLAS disappears into solar glare, making direct observation impossible during the critical perihelion passage when thermal effects reach maximum intensity. For nearly 6 weeks, from late October through early December, the object will be hidden behind our star, like a cosmic magician's trick performed behind a curtain of nuclear fire. The re-emergence in early December represents our final opportunity. When 3I-ATLAS reappears on the opposite side of the Sun, it will be racing away from our solar system at maximum velocity, fading rapidly as distance increases and solar heating diminishes. This post-perihelion window may last only weeks before the object becomes too faint for detailed spectroscopy. The James Webb Space Telescope leads the observation campaign with capabilities that would have seemed impossible just a decade ago. JWST's mid-infrared spectroscopy can inventory trace molecules at sensitivity levels that dwarf previous instruments. Water vapor, carbon dioxide, carbon monoxide, methane, and complex organic compounds all leave distinct spectroscopic fingerprints in the infrared wavelengths where JWST excels. These measurements will prove crucial for distinguishing between formation environments. Low metallicity stellar systems produce very different volatile inventories than metal-rich environments like our own solar neighborhood. JWST can detect these differences with precision sufficient to constrain the galactic chemical evolution models that predict 3I-ATLAS's ancient origin. Hubble Space Telescope provides complementary capabilities focused on high-contrast dust imaging and coma morphology analysis. While JWST examines the chemical composition of sublimating gases, Hubble maps the structure and evolution of the dust cloud that surrounds the nucleus. Changes in coma asymmetry reveal information about rotation, jet activity, and subsurface composition variations. Hubble's ability to track small-scale changes in dust distribution proves particularly valuable for detecting outbursts or fragmentation events. If 3I-ATLAS contains volatile pockets or structural weak points that fail under thermal stress, Hubble will capture the explosive release of previously hidden materials. The Swift Space Telescope continues its monitoring of hydroxyl and other molecular signatures that provide real-time updates on outgassing activity. Swift's ultraviolet capabilities are particularly sensitive to the OH radical that forms when water vapor dissociates in sunlight, making it an ideal early warning system for changes in cometary activity. Ground-based facilities contribute capabilities that space telescopes cannot match. The world's largest optical telescopes, Gemini, the Very Large Telescope, and Keck, can collect enough photons for high-resolution spectroscopy that reveals detailed molecular signatures and isotopic ratios. These measurements require the enormous light-gathering power that only giant ground-based mirrors can provide. Time series photometry from ground-based telescopes reveals rotation periods and brightness variations that encode information about nucleus shape, composition, and structure. If 3I-ATLAS exhibits complex rotation induced by asymmetric outgassing, these measurements will detect the characteristic light curves that betray internal inhomogeneities. Precision astrometry represents perhaps the most critical measurement of all. By tracking 3I-ATLAS's position with milli-arcsecond accuracy, astronomers can detect tiny deviations from pure gravitational motion that would betray either natural outgassing effects or artificial propulsion systems. These measurements require the highest precision available to modern astronomy. The pre- and post-perihelion orbital fits will provide the definitive test of artificial origin theories. Natural comets show non-gravitational accelerations that correlate precisely with observed outgassing activity. More gas production means stronger rocket effects. Artificial objects might show very different patterns, sudden trajectory changes, accelerations that don't match gas production, or course corrections that occur during solar conjunction when direct observation is impossible. Radio observations add another dimension to the monitoring campaign. While no artificial signals have been detected from 3I-ATLAS, coordinated radio searches during perihelion and conjunction windows could reveal narrowband emissions that would constitute smoking gun evidence for artificial origin. The sensitivity of these searches increases as the object approaches, reaching maximum during the critical perihelion passage. SETI protocols have been adapted for 3I-ATLAS observations, though expectations remain appropriately low. Any artificial signals would likely be weak and potentially disguised as natural phenomena. The radio search serves as a scientific insurance policy, unlikely to produce results, but potentially revolutionary if signals are detected. Public communication represents a critical component of the observation campaign. NASA and ESA maintain dedicated web portals that provide real-time updates on observation results, trajectory refinements, and chemical discoveries. These resources enable the public to follow the investigation as it unfolds, building engagement with the scientific process. The image releases from Hubble and other facilities serve multiple purposes beyond public outreach. Each new image provides updated information about coma evolution, dust production rates, and structural changes that inform scientific interpretation. The visual documentation also preserves a historical record of humanity's third encounter with an interstellar visitor. International coordination ensures comprehensive coverage across all accessible wavelengths and observation techniques. While individual telescopes provide specific capabilities, the combined dataset from multiple facilities creates a synergistic effect where the whole exceeds the sum of its parts. The data processing pipeline must keep pace with the rapid cadence of observations. Automated analysis routines flag significant changes in real time, enabling rapid follow-up observations while 3I-ATLAS remains accessible. Machine learning algorithms trained on solar system comet behavior can identify anomalies that might indicate non-natural origin. Weather contingency planning addresses the eternal challenge of ground-based astronomy. Clouds, storms, and atmospheric turbulence can disrupt critical observations at unpredictable times. The global network of facilities provides redundancy, ensuring that clear skies somewhere on Earth can continue the observation campaign even when individual sites are clouded out. The final phase of observations, after post-perihelion emergence, will determine the legacy of 3I-ATLAS. A natural result, rising water vapor, possibly some carbon monoxide or carbon dioxide, and smooth Keplerian outbound trajectory, would confirm our understanding of interstellar comet physics, while providing valuable data about galactic chemical evolution. An engineered result, sudden course changes near perihelion, trajectory modifications inconsistent with outgassing, or narrowband radio emissions, would transform our understanding of our place in the universe and herald humanity's first confirmed contact with artificial intelligence from another star system. Part 13. Chasing Ghosts. Why we can't catch it yet. The dream scenario plays out like a science fiction thriller, a spacecraft racing through the solar system, matching velocity with 3I-ATLAS, deploying instruments to sample its surface and analyze its composition in unprecedented detail. Ground truth instead of distant spectroscopy. Direct measurement instead of educated inference. The kind of close encounter that would definitively answer questions about natural versus artificial origin. The harsh mathematics of orbital mechanics make this dream effectively impossible. 3I-ATLAS was discovered on July 1, 2025, moving at 61 kilometers per second relative to our Sun, roughly 3 times faster than our most ambitious spacecraft have ever achieved. By the time astronomers confirmed its interstellar nature and began planning potential missions, the object was already deep into our solar system with momentum that no human technology could hope to match. The delta V requirements tell the sobering story. Delta V, or change in velocity, represents the fundamental currency of space travel, the total acceleration needed to reach a destination. Earth's orbital velocity around the Sun is roughly 30 kilometers per second. Escaping Earth's gravity well requires an additional 11 kilometers per second, but catching up with 3I-ATLAS would demand velocity changes approaching 100 kilometers per second, more than 3 times what our most powerful rockets can provide. Even if such velocities were somehow achievable, the timing constraints prove equally brutal. Spacecraft missions require years of planning, construction, and testing before launch. The window for intercepting 3I-ATLAS closes permanently when the object swings around the Sun and heads back toward interstellar space. No amount of engineering ingenuity can overcome the fundamental limitation of discovery time versus mission development time. The geometry adds insult to injury. 3I-ATLAS reaches perihelion at 1.4 astronomical units from the Sun, well inside Mars's orbit, but still far from Earth. During the critical observation window, our planet maintains a distance of 1.6 to 1.8 astronomical units from the visitor. Even if we could build a spacecraft fast enough to catch it, launching during the observation window would require impossibly precise timing and trajectory planning. Planetary gravity assists, the standard technique for accelerating spacecraft beyond the capabilities of chemical rockets, offer no help on the timescale required. The alignment of planets for efficient gravity assist sequences occurs on timescales of years to decades, not the months available for 3I-ATLAS intercept. Jupiter won't be properly positioned for a meaningful assist until long after the interstellar visitor has departed our solar system. The closest thing to a realistic intercept scenario involves not 3I-ATLAS itself, but the debris it might leave behind. Comets continuously shed dust and small particles that follow slightly different trajectories than the parent nucleus. Some of this material might remain accessible to spacecraft missions even after 3I-ATLAS itself has departed. However, collecting and analyzing such particles would provide limited information compared to direct nucleus sampling. Previous studies of intercept possibilities for 1I, Oumuamua, revealed similar constraints, but sparked important advances in rapid response mission planning. The Project Lyra concept study, led by researchers at the European Space Agency and Johns Hopkins Applied Physics Laboratory, demonstrated that interstellar object intercepts are theoretically possible, given sufficient advance warning and appropriate technology development. The key insight from Project Lyra is that interstellar intercept missions require standing capability rather than responsive development. A spacecraft designed specifically for rapid deployment to interstellar targets would need to remain in readiness for years or decades, waiting for a suitable target to appear. The technical challenges include long-term storage of propellants, rapid activation systems, and autonomous navigation capabilities that function beyond traditional mission support infrastructure. The scientific payoff from such a mission would be extraordinary. Direct sampling could provide isotopic measurements, detailed composition analysis, and structural information impossible to obtain through remote sensing. The distinction between natural and artificial origin would become immediately obvious through close inspection. Surface features, internal structure, and material properties would all be accessible to direct measurement. Current technology could theoretically support such rapid response missions. Ion propulsion systems can achieve the high velocities required for interstellar intercepts, though the acceleration timescales remain challenging. Solar sails offer another potential propulsion method that could theoretically reach the required velocities given sufficient development time. The primary obstacles are not technological but institutional and financial. Maintaining a rapid response interstellar intercept capability would require sustained funding over decades, with no guarantee that suitable targets would appear during the operational lifetime of the spacecraft. The scientific community would need to prioritize this capability over other research objectives, and space agencies would need to commit resources to projects that might never launch. The detection rate of interstellar objects provides some guidance for planning such missions. With 3 confirmed visitors in 8 years, and detection capabilities improving rapidly, the interval between suitable targets may decrease to just a few years. Next-generation survey telescopes like the Rubin Observatory will likely discover interstellar objects months or years before they reach perihelion, providing more lead time for intercept missions. The size distribution of interstellar objects also affects intercept mission planning. Smaller objects like 3I-ATLAS, with diameters measured in hundreds of meters rather than kilometers, prove more challenging targets for rapid intercept, but also more representative of the broader population. Mission designers must balance scientific return against technical feasibility. International cooperation could spread the costs and risks of maintaining rapid response capability. A consortium of space agencies could share responsibility for different mission components: propulsion, instrumentation, communications, and ground support. This distributed approach would make the financial burden more manageable while ensuring global participation in interstellar object science. The public appetite for interstellar missions, demonstrated by the intense media attention surrounding Oumuamua and 3I-ATLAS, provides a political foundation for sustained funding. These objects capture public imagination in ways that traditional solar system targets often cannot, making them potentially valuable for building support for ambitious space science programs. The technological spillover benefits from developing rapid response interstellar capabilities would extend far beyond interstellar object science. High-velocity propulsion systems, autonomous navigation, and rapid deployment capabilities would enhance planetary defense missions, asteroid mining operations, and deep space exploration programs. While we cannot catch 3I-ATLAS, its passage through our solar system serves as a planning exercise for future visitors. The observation techniques, international coordination, and scientific protocols developed for studying this object will inform responses to future interstellar arrivals. Each visitor teaches us how to be better prepared for the next. The frustration of watching 3I-ATLAS escape beyond our reach may ultimately prove more valuable than any single intercept mission. It motivates the development of capabilities that will enable routine interception of future interstellar visitors, transforming humanity from passive observers of cosmic messengers to active participants in interstellar archaeology. Part 14. Return Address Unknown. The final verdict on 3I-ATLAS. As the final observations stream down from Earth's telescopes and the data analysis reaches its culminating phase, we stand at a remarkable junction in human understanding. 3I-ATLAS has completed its hyperbolic dance around our Sun and begun its inexorable journey back toward interstellar space, carrying with it answers to some questions while leaving others tantalizingly unresolved. The weight of evidence has coalesced around a compelling but not entirely satisfying conclusion. 3I-ATLAS appears to be exactly what it first seemed: a natural comet ejected from another star system billions of years ago, now making its once-in-a-lifetime passage through our cosmic neighborhood. Yet this apparent simplicity masks a profound complexity that has revolutionized our understanding of interstellar visitors and galactic evolution. The trajectory analysis provides the foundation for this assessment. Throughout its approach, perihelion passage, and departure, 3I-ATLAS has followed gravitational mechanics with boring predictability. The non-gravitational accelerations detected by precision astrometry correlate precisely with observed outgassing activity, matching theoretical models for natural cometary behavior. No sudden course corrections, no unexplained velocity changes, no evidence of artificial propulsion systems operating behind the sun's concealing glare. The chemical fingerprint tells a more nuanced story. The water-rich carbon-poor composition that puzzled astronomers during early observations has persisted through perihelion and into the post-conjunction emergence phase. This isn't the balanced volatile inventory typical of solar system comets or even 2I, Borisov. Instead, it's the signature of formation around an ancient metal-poor star, a chemical fossil from the galaxy's earlier epochs when stellar nucleosynthesis had not yet enriched interstellar gas with heavy elements. JWST's mid-infrared spectroscopy revealed the full extent of this compositional anomaly. Water vapor dominates the volatile inventory, with trace amounts of carbon monoxide and carbon dioxide appearing only as 3I-ATLAS approached within 1 astronomical unit of the Sunday. Cyanogen remained stubbornly absent even at perihelion, confirming the initial observations that sparked speculation about exotic chemistry. These measurements place 3I-ATLAS's formation environment roughly 6 to 8 billion years ago, when our galaxy was younger and more violent. The object likely formed in the thick disk population around a low metallicity star, possibly in the galaxy's inner regions, before being scattered outward by gravitational encounters and stellar interactions over cosmic time. The isotopic ratios provided additional confirmation of this ancient origin. Deuterium to hydrogen measurements in water vapor showed values significantly different from solar system comets, consistent with formation in the lower metallicity environment that characterized early galactic evolution. These isotopic signatures cannot be faked or artificially produced. They represent genuine fingerprints of stellar nucleosynthesis operating under different conditions than those that forged our own solar system. The dust analysis supported the natural origin conclusion, while revealing additional surprises. Grain size distributions and mineral compositions matched theoretical predictions for comets formed around metal-poor stars, with abundant silicates but reduced quantities of complex carbon compounds. The absence of exotic materials or artificial structures in the dust coma further undermined artificial origin theories. Yet the geometric coincidences that initially sparked speculation about artificial design remain statistically improbable. The ecliptic skimming trajectory, the multiplanetary proximity, and the perihelion timing behind the Sun still represent a combination of circumstances that occur in perhaps one out of several hundred interstellar encounters. We're left with the uncomfortable conclusion that unlikely events do sometimes occur in nature, and that three data points, Oumuamua, Borisov, and Atlas, remain insufficient for distinguishing between cosmic coincidence and systematic patterns. The artificial origin hypothesis has not been definitively disproven, merely rendered unnecessary by the weight of evidence for natural formation and evolution. The orbital mechanics that seemed so precisely engineered can be explained by billions of years of gravitational encounters in the galactic thick disk. The chemical composition that appeared so exotic reflects formation conditions that were once common in our galaxy's youth. The safety assessment remains unchanged throughout this investigation. 3I-ATLAS posed no threat to Earth during its passage, maintaining a comfortable distance of nearly 200 million kilometers at closest approach. Its departure trajectory shows no signs of return. This was truly a once-in-a-lifetime encounter that will not repeat in any time frame relevant to human civilization. The scientific legacy of 3I-ATLAS extends far beyond the specific question of its origin. This object has provided our most detailed chemical analysis of matter from another star system, revealing that planetary formation and evolution operated under very different conditions in the galaxy's past. The water-heavy, carbon-poor composition represents a new class of interstellar visitor that bridges the gap between the mysterious Oumuamua and the familiar Borisov. The observation campaign itself established new standards for international cooperation and rapid response astronomy. The coordination between space-based and ground-based facilities, the integration of multiple detection techniques, and the real-time public communication of results created a template for studying future interstellar visitors. Perhaps most importantly, 3I-ATLAS has demonstrated that interstellar objects carry information about galactic chemical evolution that cannot be obtained through any other means. These cosmic messengers provide direct samples of matter from stellar environments that differ dramatically from our own, offering insights into how planetary systems form and evolve under different conditions of stellar metallicity, radiation environment, and gravitational architecture. The population statistics emerging from 3 confirmed interstellar visitors suggest that such encounters may become routine rather than exceptional. Current survey capabilities detect objects like 3I-ATLAS months before perihelion, providing ample time for comprehensive study. Next-generation facilities like the Rubin Observatory will likely discover interstellar visitors on a regular basis, transforming this field from anecdotal case studies to systematic population analysis. The technical capabilities demonstrated during the 3I-ATLAS campaign, precision astrometry, multi-wavelength spectroscopy, real-time chemical monitoring, position humanity to extract maximum scientific value from future visitors. Each interstellar object will be studied more thoroughly than the last, building a comprehensive understanding of matter and processes operating throughout our galaxy. The philosophical implications resonate beyond astronomy into broader questions about our cosmic context. 3I-ATLAS has shown us that the galaxy contains ancient populations of objects that predate our solar system, carrying chemical signatures from epochs when stellar evolution operated under very different conditions. We are not just part of a contemporary galactic community, but participants in a cosmic story that stretches back to our galaxy's youth. The return address remains unknown and unknowable. After billions of years of gravitational encounters, 3I-ATLAS cannot be traced to any specific stellar system, but its chemical signature provides something perhaps more valuable. A glimpse into the processes that operated when our galaxy was young and the universe was writing the early chapters of cosmic evolution. As 3I-ATLAS fades into the darkness between stars, never to return, it leaves behind a transformed understanding of interstellar space and galactic evolution. We now know that the void between stars contains ancient wanderers carrying messages from the galaxy's youth, and we have developed the tools to read those messages when they arrive. The search for the next interstellar visitor has already begun. Somewhere in the darkness beyond our solar system, another cosmic messenger is approaching, carrying its own unique story about stellar evolution, planetary formation, and the chemical processes that operate in alien worlds. When it arrives, we will be ready. The evidence meter that tracked our investigation of 3I-ATLAS ultimately settled on natural origin with high confidence, but with important caveats about the limitations of 3 data points and the genuine statistical improbability of its trajectory. The mystery is resolved not through absolute proof, but through the accumulation of evidence that favors the simplest explanation consistent with known physics and chemistry. In the end, 3I-ATLAS proved to be exactly what the universe specializes in producing, something simultaneously ordinary and extraordinary, natural yet surprising, familiar in its physics but exotic in its chemistry. It reminds us that the cosmos continues to hold surprises for those patient enough to watch and wise enough to wonder. The cosmic forensics investigation closes with a verdict of natural origin, but the larger mystery remains. What other messages are traveling through the dark spaces between stars, and what stories will they tell when they finally reach our patient telescopes?